Physics students, good afternoon. Today in this video what we're going to be looking at is a sample problem over projectile motion. Now this video is primarily going to be for those of you that missed class due to the PSAT, so we're going to quickly cover over kind of what we talked about in class today. So where we began our study of projectile motion was looking at how objects travel both horizontally and vertically at the same time. Now, for today's video, we're going to be looking at what happens when an object is not on flat level ground, but when it's maybe falling from a surface, something like a desk. So, we're going to call this sample problem the rolling object. And how we're going to model this is another kind of classic projectile motion scenario, is that let's just imagine a tennis ball is going to roll off the edge of my desk. Something like, let's say this. Rolls off the edge and falls to the ground. So, we'll draw in here my desk. We'll assume my desk is about, let's go 1.5 meters off the ground. Probably a little bit taller than what it actually is, but we'll go with about 1.5 meters. Now our tennis ball, we'll say has an initial velocity, V0, of 5 meters per second. And like we've talked about with projectile motion, whenever that ball falls off the edge, it's effectively going to fall down until it strikes the ground. So we are kind of our ground down here. Now with regard to projectile motion, what we are oftentimes interested in is how far our object is traveling and how long it takes to get there. So those are the two questions that we're going to examine. One, how far it travels, and two, how long it takes to get there. Now, as we've seen is really important when we're dealing with kinematics or even projectile motion, we need to connect what we're looking for to a variable so we can know what we're solving for here. So how far, we're looking for its delta x, the range, effectively, that horizontal distance, and how long describes our time. Okay? So, let's take a minute, now that we have our picture, kind of have a visual of what we're doing here, to list out the variables that we know. So, in the x direction, I don't know my delta x here. I'm not sure how far I'm traveling, but I'm going to put a star here so that I know I'm going to come back and try and solve this. I don't know my initial velocity just yet. I don't know my final velocity, but I always know my acceleration in the x will be 0 meters per second squared, and I also don't know time. So it doesn't look like I know a whole lot of what's going on in the x direction. Let's take a look at the y. Now my delta y, how far my object travels vertically. Well, that's going to be really the height of my desk here, 1.5 meters. But don't forget, we wanted to find its displacement. So the final minus the initial, or we can also look at where the object travels. It's going downward, so it should be a negative 1.5 meters. Now my V0 and the y, my initial velocity, I don't really know. We're going to come back to that. Our V1 in the y, we also don't know. Our acceleration in the y, negative 9.81 meters per second squared, and then we have time. Now, one important factor that we do know about time, it is going to be the same in both directions here. So for whatever point we choose, it's going to take the same time to travel vertically as it is horizontally. Okay. So at this point, it doesn't seem like we have a whole lot of information. But if you remember from our picture, we're not taking into account this velocity of 5 meters per second. And as that object is rolling on a flat surface, you can imagine, when it just comes off of that surface, it has an initial velocity of 5 meters per second. But initially, that's only going in the horizontal direction. Then, just briefly, after it kind of falls off the edge, gravity is going to start to have an effect and pull that object downward. But as we talked about, velocity in the x direction is still going to be essentially moving that object forward. So this velocity initially, 5 meters per second, you'll notice, is all horizontal. So what that means for our variables is very important. My V0 in the x direction is 5 meters per second, and my V0 in the y is 0 meters per second. That is because we are rolling off of a flat edge, a flat surface, if you will. Now, one thing that we've talked about is that we're going to model these scenarios with projectile motion as if our acceleration in the x direction is 0. So our velocity is not going to change. meaning if I start at 5, I'm going to end at 5. Now, at this point, we know a lot more information than we initially thought. We were only given kind of two numbers here, a height and a velocity, but we've translated that into what looks like almost 6 variables. So remember, when we deal with projectile motion, we're going to know more than we think right off the bat. So in order to solve for my time, I'm probably going to go with the y direction here. We talked about this a little bit previously, that if we go in the x direction, all our numbers are telling us is that our velocity is always 5. So we don't really know how far we're going to go or how long it's going to take us to get there. We just know we're always moving at 5 meters per second horizontally. So we're going to start with this y direction to try and find time. So that means I'm going to ignore V1. We're not going to be too concerned with it. And if I look at my kinematic equation sheet, time doesn't appear, or excuse me, V1 doesn't appear in equation 2. So let's go there. Delta y is equal to my initial velocity in the y direction times time plus 1/2 acceleration in the y times t squared. Now at this point, I know that my initial velocity in the y was 0 because it was just rolling off that flat surface. So this value is all going to go to 0. Doesn't matter what my time is here because my initial velocity, 0 times t, is going to give me 0. So my equation will simplify down to this. Delta y is equal to 1/2 acceleration in the y times t squared. So now that I have a more simplified version of my equation, I'm just going to plug some numbers in. Our delta y was negative 1.5 meters is equal to 1/2 times negative 9.81 meters per second squared times t squared. So 1/2 times negative 9.81 is going to give me approximately negative 4.91 times t squared. So again, we're trying to use the y direction here to find time. So to get that time by itself, I'm now going to divide by negative 4.91. And again, this is where we can see why it's important that our initial delta y is negative. Because if I don't do that, I'm going to eventually have a negative value that I'll have to take the square root of, which is going to give me a non-real answer, which I really don't want. So these negative 4.91s will cancel out, and I'll be left with an equation that looks like this. T squared is equal to negative 1.5 meters divided by negative 4.91 meters per second squared. So if I plug that in real quick to my calculator, I'm going to get a time value squared of about 0.305 seconds squared. But don't forget, to get time just by itself, I'll eventually need to take a square root of both sides of my equation. And when I do, we get a time value of approximately 0.55 seconds. So that means it takes about half a second for that ball to reach the ground, falling off of my desk that's about 1.5 meters tall, which makes sense. We shouldn't be getting a value for time here of 20 seconds. It's probably not going to take us that long to get there. So let's come back to our variable list. I'm going to write this in. T is 0.55 seconds, and that's going to be the same for both directions. 0.55 seconds. So that's the first part of our question. We now know how long our object's going to take to get there. The second part is that I want to find how far it goes. And one thing we discussed is that when we have 4 variables, we can probably use any equation to solve for that delta x. But equation 2 actually works the best because it becomes much more simplified in the x direction. So let's come back and look at equation number 2, see if we can find how far. Looks like this. Delta x is my initial velocity in the x direction times time plus 1/2 acceleration in the x direction times t squared. Now, because we're going to assume acceleration in the x direction is 0, all of this value over here is going to go to 0. So 0 times t squared times 1/2, doesn't matter what my other values are, if there's a 0 in there and I multiply some other things with that 0, it's always going to be 0. Which is why equation 2 is great to use because it simplifies down to really just this in here. Delta x is v naught in the x times time. So I'm just going to take the values that I know. My v naught in the x was my 5 meters per second, and I'm going to multiply by my time of 0.55 seconds, something we just solved for. So I'll take this value, I'll plug it in, and I get a delta x of about 2.76 meters. So now we've gone through and solved for the second part of what we're looking for. We now know how far our object travels, and 2, how long it takes to get there. And so, important things to remember here. If I'm traveling just off the edge of a flat surface, my initial velocity in the y direction is always going to be 0. And when we deal with projectile motion, and you'll hear me say this a lot, we always know more than we think. Hopefully, this gets us kind of going in the right direction and understanding how we can analyze a different type of projectile.